Hi, everyone. In this video, we are going to be talking about two statistics that are going to help us when we are looking at sets of data or looking at any sort of figure or graph the rest of this year. And those two statistics, as you may have guessed by the title, are going to be standard deviation and standard error. So let's start off by looking at this graph. I don't think it's a real graph, it's just for an example, but I found it online and I think it gets across the point that I'm going to try to make. So when we look at a figure like this, there are certain conclusions that I think that we would all feel comfortable making. So I think we would all feel comfortable saying that according to this data, people like blueberries more than they like grapes. But there are also some questions that we could have after looking at this graph as well. So maybe we're looking at apples and oranges. And one question that we might have is it looks like people slightly prefer apples to oranges, but um, we could wonder whether that's a real difference or whether that's just sort of noise in the sample. Maybe if we ran this experiment again and asked a different group of people, apples and oranges would be exactly the same, or maybe oranges would even be slightly ahead of apples. So is this a real difference or not? We could also wonder about how if this same question, like what's the nicest fruit, was asked to multiple groups of people. Let's imagine that they did this experiment in Seattle and in San Francisco and in Boston and in a couple other cities as well. Would you get the same answers in different places? And sort of what is the variability in this data? So we can imagine looking at this data. Let's imagine that each of these numbers represents the number of people who said that fruit was the nicest in different cities. So maybe 25 people in Seattle said kiwi was the nicest, but if you go down to San Francisco, 80 people said kiwi was the nicest. And over in Massachusetts, only 5 people said it was the nicest. Um, but for grapes, we're getting much more consistent data. Wherever you go, Seattle, San Francisco, Boston, only 5 people are saying grapes are the nicest fruit. So this sort of idea of the consistency in a set of data, we don't get that from looking at this graph. Um, if you average the people who said grape was the nicest, it's still 5, so that's still an accurate representation here. And if you average these numbers for the Kiwis, it would come out to 25. So this graph is still a representation of these two data sets, but we can see, looking at these numbers, that these data sets aren't the same. There's a lot more variation for Kiwis than there is for grapes. So the first statistic that we're going to talk about, standard deviation, is just a way to sort of capture what's going on with these numbers here. So standard deviation shows how much variation there is from the average or the mean in a set of data. And if the data points are close together, like the extreme example would be these grapes here, there's no variation, they're all exactly the mean. So if the data points are close together, similar to those grapes, the standard deviation is going to be really small. And if the data points are spread out, then the standard deviation is going to be larger. So bigger standard deviation means the numbers are going to be sort of more all over the place, like they are in this Kiwi data set. So when we're thinking about standard deviation, it's going to be most helpful if our data is normally distributed. And that just means that it's going to fit into this nice bell curve here. We can't actually assume that all of our data is normally distributed, but for the purposes of this class and for simplicity, we're just going to make that assumption about all of our data. So this bell curve will come back into play a little bit later. So let's dig a little bit more into standard deviation. So this formula is ugly looking unless you really like looking at symbols in your math, which I personally don't. But I just thought it would be helpful to go through how you calculate standard deviation, even though you are never going to have to calculate standard deviation in this class by hand. So anytime I'm going to ask you to think about standard deviation, it's more going to be, are you able to apply it? Are you able to analyze graphs using standard deviation? Do you understand what it means? But I think it might be helpful to work through an example problem where we find the standard deviation, just so you have a better sense of, like, if you calculate it and you go to an online calculator, where is that number coming from? So if we look at the formula here, there are sort of three to four main parts. So one bit is right here, and that's where we're going to be taking the difference between any individual measurement that we might have and the average of a sample. So that's this bit right here, and then we're going to square that number. We're going to do that for each measurement that we have in our sample, and then we're going to add up all of those together. We're going to divide it by the number of uh, measurements that we have minus one. And don't worry about, like, why it's minus one. We'll just take it as a given that it's minus one. And you can ask Christine if you want to understand the whys more. So we're going to divide by the total number of the sample size minus one, essentially, and then we're going to take the square root. So let's see what this looks like in practice, in an example. So we can imagine that we have 10 people who took a quiz, and these are the grades they got. So the first step to figure out standard deviation is to find the mean. So you could do that by hand, you could use an online calculator, but if you went and found the mean of these quiz scores, you would find that the mean is 86.9. So the next step, you might remember that I said we're going to figure out the difference between any given measurement and the mean. So we're going to look at all of our quiz scores individually. So our first score is 96. So we're going to find the difference between 96 and the mean and square it. Our second score is also 96. So again, we're going to take 96, subtract the mean, and square it. Our third score is 93, so we're going to take 93, subtract the mean, and square that. And we're going to do that for each of the members of our sample. So we're going to do that for 88, for 86, 86, 84, 80, and then finally we're going to do the same thing for 70. So 70 minus the mean and square it. We're going to add up all of these numbers, and the sum, if we did that, would be 556.9. So we've just taken care of this top part of the standard deviation equation. The next step is to figure out what number is on the bottom here. So we have 10 people who took the quiz, so our sample size is 10. And for this formula, we're going to subtract 1 from our total sample size. So 10 minus 1 is 9. So we have 9 what's called degrees of freedom. And you don't need to remember that name or that word. It's going to pop up again. So I'm just saying it now so that when you hear it later, it doesn't sound so unfamiliar. So basically, we're just going to put 9 on the bottom of this equation here. So 556.9, which is what we added up here, divided by 9, which is what we calculated here. And if we did that, we would get 61.88. And then finally, the last step was to take the square root. And so we're going to take the square root of 61.88. And if we did that, we would get a final number of 7.9. So the two big pieces here are our mean, which is, let's just say 87 for simplicity, and our standard deviation, which let's just round this up to 8 again for simplicity. So the fun thing about standard deviation, once you've calculated it, is what you can infer based on this bell curve here. So we can sort of pin different percentages of our measurements within this bell curve based on standard deviation. So our mean is right here in the middle of the bell curve. And if we go up 1 standard deviation to right here, and also down 1 standard deviation to right here, then we can say that 68% of our data should fit within this range from here to here on the bell curve. So for our quiz scores, that would be our mean of 87. So we could subtract 8 to find this sort of lower bound right here. And we could add 8, so 87 plus 8, to find our upper bound right here. And then, so that would give us 87 minus 8 is 79. 87 plus 8 is 95. So we're looking at between 79% on the quiz and 95% on the quiz. And we would say that 68% of the people in that class should be between those two scores, between plus or minus 1 standard deviation. We can do a similar thing for 2 standard deviations. Since 1 standard deviation is 8, 2 standard deviations is just going to be double that, so it's going to be 16. So we can do 87 minus 16, which is 71. And then maybe there's a lot of extra credit on this quiz. 87 plus 16 is 103. So that's taking us to the range of 2 standard deviations. So 1, 2, our lower bound is right here. That's that 71%. And then from our mean up 2 standard deviations is right here. And that's going to be this 103%. So you can see down here below, 95% of our quiz scores should fit between those two numbers within that 71 to 103% range. And then we're not going to really do anything with 3 standard deviations, but you can do a similar thing with 3 standard deviations, and you'll get 99.7% of your data within those plus or minus 3 standard deviations. So, all of this, let me just make sure. Yeah, all of this information, it all kind of depends on what our mean is. Like our center point, we're going out from there, right? Plus a standard deviation or two, minus a standard deviation or two, but it's all coming from the mean. So, a big question that we have to ask ourselves is, how confident are we that our mean is accurate? Do we feel confident that the mean that we calculated based on whatever experiment we did, do we feel confident that that's like the true mean? So if we did the same experiment a million times, would we get a mean that's really similar to what we calculated? So when we're thinking about what might affect the accuracy of a mean that we find for an experiment, there are two big things that kind of might affect that. So, one is the sample size. If we have a big sample size and we have a lot of data points, then that's going to be a large sample and we're going to feel more confident in our calculated mean. But if we have a small sample size, and maybe we only just took a few measurements, then we're going to be less confident that the mean that we calculated is accurate. The second thing is variability. So if we have a lot of variability in our data, maybe our data looked more like that kiwi sample in the fruit graph, then we're going to feel less confident that whatever mean we got is the true mean. So we got 25 people liking kiwi out of a sample of 145 in that original graph. But if we asked every city, I don't feel super confident that 25 is exactly what we would end up with again. But if there's lower variability, like the grape, maybe we feel more confident that that data is accurate. So for grapes, we asked in 6 different cities, and in every single city, 5 people said they liked grapes. So I think we feel more confident that it's around 5 out of 145 people that are a fan of grapes as the nicest fruit. Okay, so to sort of capture this aspect of how confident we're feeling in our mean, we're going to use our second statistic of this video, which is standard error. It's called standard error or standard error of the mean. So if you see either of those, SE or SEM, standard error or standard error of the mean, it's the same thing. And we use this to represent uncertainty in an estimation of a mean, uncertainty in the mean that we calculated. It accounts for both sample size and variability, the two things that we talked about on the previous slide. And for this, since we're thinking about it as an amount of uncertainty, if your standard error is smaller, then you feel more confident that your mean is accurate. So a smaller amount of uncertainty, you're more confident that your calculated mean is accurate. If your SEM or standard error is larger, that's like a larger amount of error, then you're less confident that whatever mean you calculated is an accurate estimation. So, smaller standard error, more accurate mean, larger standard error, you feel like less confident that your mean is accurate. The formula for standard error is shown right here. And again, you won't have to calculate this by hand, but I'm just showing you what it is. You find standard error by taking the standard deviation and dividing it by the square root of your sample size. So for our example previously with the test scores, where we had a mean of 87 and a standard deviation of about 8, if we did that, our standard error would be about 2.5. Okay, so we can use both standard deviation and standard error to make error bars on a graph. And that's primarily what we're going to be using these two statistics to do. So when you're looking at a mean, usually you're going to represent it with either a dot if it's a scatter plot. So like these are all means right here where the dots are. Or it's like sort of the top of a bar chart if we're doing a histogram or a bar chart. The mean would be sort of the line at the top of the bar. And when you add error bars, your graphs are automatically going to look 1,000 times more fancy. So we're going to do that. And it also gives you more information about the data itself. So the error bars are going to go above and below the mean, and they could mark either standard deviation. It could be one standard deviation or it could be two standard deviations. They can also mark standard error. So it could be one standard error or it could be two standard errors. So if you're reading a chart and it has a figure like this, ideally there should be a caption underneath that tells you what these error bars represent. And the length of the bars is going to is going to represent different things depending on whether the error bars are representing standard deviation or whether they're representing standard error. So if they're representing standard error or standard error of the mean, the error bars are showing the reliability of that average that they've calculated. So we could say if these bars were standard error, that we feel more confident in this mean because the bars are shorter than we do in this mean because the bars are larger. If the bars are showing standard deviation, then the error bar size is going to show how tightly clustered that data is. So we could say that for this one, the data was more tightly clustered. People who were doing 20 jumping jacks had somewhere really close to 122 beats per minute heart rate. Whereas if they only did 5 jumping jacks, there was more variability in that data. People were between, they were in the range of 90, but there was some higher and some lower. So that's the sort of error bar aspect is what we want to focus on. And I want to sort of zero in on the next slide, and I promise it's the last one, about if we're using standard error bars, to what we can infer based on standard error bars. Okay, so when we're graphing means, and here we're showing a bar chart instead of a scatter plot, but the same principles are going to apply. We can use that standard error that we calculate to add error bars to our graph. And if we use specifically plus or minus 2 standard errors, this is going to give us what's called a 95% confidence interval. And I care less about the 95% confidence interval. You can kind of like ignore that language. But this next bit is what I really want to sort of hone in on. So what you should pay attention to is if you're looking at a graph that's using plus or minus 2 standard errors as the error bars, you can tell a lot based on whether those error bars overlap. So if we look at, what's a good example? If we look at these two bits here, C and D, you can see that the standard error bars for C and the standard error bars for D, they overlap with one another. So like D's range goes here and it goes here, and it's like overlapping with the range for C, which is going here and here. And in that overlap, the mean of both of them is included. So the mean for D is in the range for the error bars of C. And the mean for C is right at the bottom, but it's still within the range of error for graph D. So when this happens, when the range of bars is overlapping one another and it includes the means for both, this indicates that there's probably not a difference between the two data sets, or at least not a significant difference. We can't say that there's a difference based on this data. So even though it maybe just looks like D is higher, and if you didn't have the error bars, you might say, oh, D is higher than C. With the error bars, we can't say that that's a real difference. So we have to say, statistically, there's no difference between them. However, if the error bars do not overlap, so an example of this is between D and E. So D's error bars are here, and that bottom bar isn't overlapping with the top of E. So there's no overlap between these sets of bars. If that happens, there likely is a significant difference between these two data sets. So we can say there's a statistically significant difference between D and E. So this is what I know this was like a lot of math and statistics for the beginning of the year, but I really want us to be able to look at graphs critically and talk about and talk with some insight to back it up about whether there's a difference between two sets of data. So based on this, we could say there is not a significant difference between C and D, but there is a significant difference between D and E. So hopefully this gives you a sense of, I'm just going back to our fruit, our fruit graph. Hopefully this gives you a sense of how useful error bars in a graph can be. Without error bars, we really have no way of saying whether apples and oranges are statistically different from one another. We also have no idea about the spread of the data, about how much variability there is. So with error bars that indicate standard deviation or standard error, we can get a lot more information from any given figure. Okay, I know that was a lot, so I will leave it at that, and I'll see you all soon.